In this video, we're going to see how to do regression in SPSS. We're going to start off with simple linear regression, but when we come down to analyze and regression, we can see there are a lot of options under this particular category, and a number of ways of doing various types of regression. And for right now, we're going to focus on simple linear regression. And what we want to do is look at refractive error regressed on years before myopia. So we have our dependent variable up here. That's going to be the refractive error. And then we have independent variables. We can have, in multiple regression, we list a number of things. In a simple linear regression, we just have one option. We can add a selection variable here if we want to. You usually don't do it at this point, but in this location, rather use data select, but that's just me. You can do it at that point. We also get to choose some statistics, although most of these are really relevant for the multiple regression. So we could add descriptives, which would give us the means for our variables, and we could do case-wise diagnostics, which are helpful if we want to identify outliers outside 3 standard deviations. The typical approach here is to identify those outliers, then change the data, trim the observations by setting those values greater than 3 standard deviations to 3 standard deviations. And in fact, to facilitate doing that, we can click on descriptives. We can have some plots, though. Honestly, you probably won't do too many of these plots. There are other plots that are more useful that we'll discuss. You can save things. For example, you can save the computed predicted value. Y equals a plus bx. When you get the a and the b of the intercept and slope, you can plug in and calculate the y. This does that for you. Residuals, same thing. The difference from the observed value minus the predicted value is the unstandardized residual. That's the error term in regression. Standardized refers to a z-score standard, so you take that unstandardized, divide it by the standard deviation of the residuals, and you get a standardized value. Studentized uses the student t-test instead of the normal distribution. Again, more things. The influence statistics say to the degree that one particular observation is impacting on the whole curve. That's why we do the trimmed values, so that individual numbers don't have such a big value. Then we can give prediction intervals for either the mean, the line that is, or the individual observations. And we can create a file of these coefficients. Style. Honestly, I don't use this, so I don't even know what to tell you about this. All right. Did we save our residuals? No, we want to save our studentized residuals. Okay. So this is what our output looks like. See, it's pretty fast. I did not pause the tape. So up here, it gives us our descriptives, tells how many Asians there are. And in this case, since init years is only available for myopes, we only get myopes in this study. The emmetropes, we did not filter out for emmetropes, but they did not show up because of the missing data. So we get our mean and our standard deviation for refractive error for years of init years. The mean under init years kind of tells us, and the standard deviation gives us an idea if we're following them the same amount for each ethnic category, which appears that we are. We get the correlations between refractive error and years of onset. That's minus 0.871 for the Asians. It says whether or not it's significant, the n that goes into that. Variables entered and removed. Well, there's only one variable here, so they're all basically going in. Model summary, remember for Asians, our correlation was 0.871. There it is there as well. And if you square that, you get 0.759. Adjusted is going to be the same. This is adjusted based on the number of variables. So the more variables you enter, independent variables you have, by definition, the R-square goes up. So this adjusted R-square reduces the amount of variance accounted for by your model to line up as though you were only looking at one. And then this is the standard error of the estimate R-square. In here we have an ANOVA, gives the overall p-value for our model. Again, in this case, it's going to be the same as the coefficients because there's only one variable. And then finally here we have the table with the coefficients. So we have our four ethnic categories. We have the constant that in y equals a plus bx, that's the a. The b under the years before and after, that's the slope. This is the intercept, this is the slope. These are the standard errors of the intercepts and slope. This is a standardized coefficient known as beta. If you divide the b coefficient, the slope, by the standard error, you get a standardized coefficient. And that's the purpose of this, is to kind of give you an idea when you have multiple variables. This b can be a number that varies because of the size of the independent variable scale. This standardizes it so you can see how they are and how they compare against other variables. And in this case, you can see that they also show that the weight is pretty constant across the different ethnicities. This is a T that shows the significance of the coefficient. It does it for both the intercept and coefficient or slope. The T is equal to the unstandardized B divided by its standard error, and you get this value right here. And that's significance. So here we have our case-wise diagnostics. This shows which variables are, or which observations, case number 68, is at -3 standardized residuals. So this would be an outlier. So we could go in and replace the refractive error for number 68 with 3 times a variable that is the mean. If this person's Asian, we would look at their ethnicity, and then we would replace it with the mean plus 3 times the standard deviation. That would be the new value. That's a trimmed way of handling outliers. You can see there's a few. Our residual statistics, we're not really going to go into right now, but these give you lots of information on the various influence and the like. This is for another video. All right, that's how you do regression. Oh, one more thing I should show you. If we go to the end here, we get our studentized residual for the refractive error. So this first observation was minus 1.37 standard T's away from the predicted value. It was under. The observation was less than predicted. This 0.37 was 0.37 t's above it. It's like a z-score, like a standard score, only it's based on t. In this case, the t and the z are very close because the sample size is so big. So that's it.